Hey there, welcome to a video discussing the Chapter 5 test review problem set. Here we are working through numbers 1 through 4, which deal with verifying identities. You're being asked to show all steps. And typically, as a good practice, you'll want to work on only one side. Actually, there might be even a requirement to work on just one side of the identity. Remember, these are called identities because the left side and right side are identical. So regardless of what you plug in for theta, the left side and right side always equal each other. For example, like 2 times x plus 1 is the same thing as 2x plus 2, right? That's an identity because the left side will be identical to the right side regardless of what you plug in for x. So again, as I said, a good practice, you're going to work on one side, and usually this side's more complicated. Another good practice is to convert anything that's not sine or cosine to sine or cosine. So cotangent, for example, is 1 over tangent, but I'm not sure if that'll help us too much. So what I probably would do is convert the cotangent to cosine over sine instead of 1 over tangent. Remember, tangent's sine over cosine, but cotangent's cosine over sine. And of course, secant's 1 over cosine. And the right side I'll leave alone. And fortunately, we see that those expressions cancel, leaving you just 1 over sine theta equals the other side. And 1 over sine theta, of course, is cosecant theta, so you can go back to something that's not in terms of sine or cosine, and now it's verified. Now we're okay. Okay, let's keep on moving. So if we look at number 2, here you have another identity. Probably not quite clear what side's the best side to work on, but I'm going to work on the left side just because there's a minus operation. So I know that's going to be 1 over sine u, and I'm going to write this minus sine u over 1. And if you feel like you're spinning your wheels, then you could obviously redo and do the right side. So the LCD here, of course, is sine u. So you have to multiply top and bottom by sine u. If you do that, you wind up getting 1 minus sine squared u. And down below, you get sine u. The other side, again, remember we left alone. Now, hopefully you recognize that this is another identity. Remember, cosine squared plus sine squared equals 1. And if you move the sine squared over to the other side, then cosine squared u equals 1 minus sine squared u. So you can make that cosine squared u over sine u. If you're a little more crafty with your algebra, the cosine u can be broken apart like this. And divide the whole thing by sine u. And all of this we know is just going to be cotangent. So you can break it off just using, good fraction arithmetic. Like, for example, if I have 4 times 5 over 6, I could break it apart as 4 times 5, 6. There's nothing wrong with that. You could totally do that. So that's exactly what I did here. And cosine over sine is cotangent. So obviously this one's much longer than the previous one, but we have it verified. Could I have worked the right side? I could have. I could have converted the cotangent to cosine over sine and have cosine squared up top. I'm trying to rack. Yeah, I guess you could have, and then convert the cosine squared to 1 minus sine squared and continue breaking apart the fraction. So you could have worked on the right side too if you wanted to. I think it would just be just as lengthy as what I just did right now. But you could have worked on the right side. Again, by converting this to cosine over sine. And then you have cosine squared over sine u. And you have 1 minus sine squared u over sine u. And then you could break apart that fraction as 1 over sine u. Okay, now I just wind up doing the alternative way I didn't want to. I just did. And then you wind up getting cosecant and sine. Okay, we'll keep on moving. Let's look at 3 and 4. So for number 3, it's pretty obvious the left side is more complicated. So let's factor out a cosine x. And it's 1 minus sine squared x equals cos cubed x. And fortunately, we know that this right here is already cosine squared x. So you got cosine x times cosine squared x equals the right side. And that's cosine cubed x. So that was actually a pretty easy one. Done. For number 4, again, not terribly obvious which one might seem more complex, but actually, we'll work on the left side. I think either way, you'll be fine, whichever way you choose. But if you work on the left side, you're going to have 1 over sine x plus cos x over sine x equals the other side. And that's going to be cosecant x plus cotangent x. And there you go. So 2 is definitely more complex than the other 3 here. Here you're being asked to find the exact value of the expression. So you're going to have to use your sum or difference formulas. Now, for 15 degrees, I could do 45 minus 30 degrees, right? So I could think of this as cosine of 45 degrees minus 30 degrees. And there's a formula that says that if we have cosine of A minus B, that's totally going to be cosine of A times cosine of B minus sine of A. Actually, I'm going to say plus sine of A times sine of B. Obviously, I've been doing this a long time. I have it memorized. I know you guys don't, so hopefully you'll get the formulas. So if you do this, you should get cosine 45 degrees times cosine 30 degrees plus sine 45 degrees times sine 30 degrees. I know that's root 2 over 2, so it's unit circle stuff for sure. That's going to be root 3 over 2. That's going to be root 2 over 2. And that's going to be 1/2. So you're only getting root 6 plus root 2 all over 4. Because that's root 6 over 4 over here. And it's root 2 over 4 over here. Now you could verify this if you were to take a graphing calculator and do the cosine of 15. Make sure you're in degree mode. I think I get 0.965 or 0.966 when you round to the thousandth place. I do root 6 plus root 2 and divide by 4. I do get 0.966. So I know I've done it correctly. Now for number 6, tan of 255. Again, you're tasked to find 2 angles that add up to 255 or subtract to 255. I believe I could do 135 and 120. Those are both on the unit circle. So we got tangent of 135 degrees plus 120 degrees. Now, there's a rule that states that when you have tangent of A plus B, that's tangent of A plus tangent of B all over 1 minus tangent of A times tangent of B. So that's what we're doing here. Tangent of 135 plus tangent of 120 degrees over so that's 1 plus, and now tan 120, sorry, -1. That's going to be negative root 3 over 3, I think. No, negative root 3. That's 1 minus parentheses -1 plus negative root 3. So when you work this out, you should get 2 minus root 3. Okay, so I'm noticing an error with my work here. I was supposed to be multiplying these two together, so my apologies for that. So that does change things a little bit. That will be 1 minus root 3 down here. So you have negative 1 minus root 3 and 1 minus root 3. And I'd probably just leave it like that. You don't really need to do much work with that. Now, if you were to work out tan of 255, you do get 3.73, and it's in the third quadrant, so it should be positive, 3.732. If I do negative 1 minus root 3 divided by 1 minus root 3, you do get 3.73. So I know it works out. Okay, now let's do number 7, then I'll do another recording for the other parts. Looks like there's some solving and more verifying identities. And some interesting problems here, 8, 9, 10. So for number 7, sine 75, that's pretty easy. That's 30 plus 45. So sine of 30 degrees plus 45 degrees. Now the formula for the sum formula for sine is sine A plus B is going to be sine A times cos B plus cos A times sine B. Right? So we work that out. So you have sine 30 degrees times cosine 45 degrees plus cosine 30 degrees times sine 45 degrees. Well, that's going to be half times root 2 root 2. That's going to be root 3 root 2 times root 2 root 2. So we actually get the same result as we did for number 5. Root 2 plus root 6 all over 4. And it's interesting because 15 and 75 are complements of each other. Cos 15 should equal sine 75. And that's actually yet another identity. Sine of an angle equals a cosine of 9 degrees minus that angle, assuming that you're working at degrees. Or if you're working with radians, then pi over 2 minus theta. That'll always be true. And likewise, if I did cosine of theta is the same thing as sine of pi over 2 minus theta, or 9 degrees if we're working at degrees. So shouldn't be surprising that we got the same result between 5 and 7. Okay. So I'll do a part 2 for this recording in a little bit.